Hi guys. Um, okay, so thanks for coming. Lots of people coming to say hi. It's a pretty interesting, cool topic. Uh, and so what we're going to be talking through today is reliability and maintenance with an example. So as you know, NDAs can't really talk about clients and their data sets, but we did get one client data set to look at. And so what we're looking at today is how is reliability and maintenance done now, and how can it be improved? Like, what's the stuff that we've been doing to get machine learning into R&M teams? Um, and so just as a high level introduction to the topic, there's a lot of detail. And so we're going to go through a bunch of terminology. You can reach these slides at rul.lemay.ai. I'm going to go through the technical terminology relatively quickly because it's highly Googleable, standard in the industry. Um, and so what this field is about is looking at the failure of parts and trying to predict when those failures are expected to know, hopefully in advance, what to fix or replace or have spare parts for. And so that's the big picture. Looking at the failure history and other stuff to figure out what to do. Um, okay, so um, R&M teams do a good job of this, but maybe it can be done a bit better. Um, and so the way that this is done now is a combination of uh, testing in labs that create spreadsheets and then following those spreadsheets failure curves. Also statistics models that are trained on data. And so it's not like this field was born yesterday. It's actually a reasonable field already. But deep learning is new and fancy. And so this is how things, how things look now. You've got critical components that you do some lab testing to say, like, how many mating cycles is this part expected to work, um, and then you have some expectation of when's the end of life of the part, and also some kind of expectations about degradation in terms of use and lifespan. So like on shelf lifespan if you do nothing, and also through use. But maybe we can do better. Um, if you think about it, a bar of steel in the ocean is not the same as a bar of steel in a dry warehouse. The data sheet doesn't know about what's happening. And so maybe we can do better. That's a very high level idea of what do I mean by do better. Maybe we can take data that we know about the parts in the field and how they're failing in the field, train a machine learning model to make predictions about this stuff. So that's like in science land. And if the math looks good, then we could deploy that solution to help the R&M team and the actual operators to do better at uptime. And so we have to be a little bit cautious about like under promising and over delivering. The idea here is that we're trying to make a model of something that's very complicated. And as long as that model is better than what we have now, that's an improvement. So we'll talk a little bit later about metrics, but the big picture is we're just looking to better predict faults, failures, replacements, so that we can manage our fleet. And so the example that I'm going to walk through with you today is a brain stimulator by a company called Neuraleve. So I've been involved in this for over 10 years now. It's a Health Canada approved medical device. It's got CE certification as well, ISO certification. And so it's a representative example of a complicated system that has like a bill of materials with lots of parts and subparts. Um, and this is the kind of project that we do where you have a fleet of vehicles or drones or medical devices, something that's like highly regulated and complicated that you want to model. How is it going to fail and how should you fix it? And it's not like a disposable thing where you just go, I'll buy more. What we want to do here is have high availability of assets. We want to be cost efficient. Like having a million parts on the shelf is one way to solve your having high availability problem, but that's not realistic or smart. And we also want to have some predictability. So failure in the field is not good. We want to avoid that and do, proactive actions to keep uptime going. So again, you can see through this like kind of explodey view of this device, it's not a monolithic unit. Like a vehicle or an aircraft, it's got a million little parts on it. Each of those parts has their own possible things that can go wrong. And what we tend to see is that these devices that we're doing work on, whether they're a vehicle or whatever, they tend to not be new. They have like a real long history to them. So this device has been Health Canada approved since 2015. And so different things, as we'll see, go wrong, and you want to be able to mitigate those things. So these things tend to come as systems. They don't come as like a unit that's isolated, that does its own job. They're highly integrated with other systems. So a vehicle may be part of a fleet of vehicles, or an aircraft may be part of a fleet of aircraft. Similarly, when you have a medical device like this, it's part of a larger mechanical, electrical, and logistics system, and the failures can kind of cascade. So here we're looking at a battery charger. If the battery charger fails, kind of the system failed if you don't have another battery charger. So yes, it's not technically part of the enclosure of the bill of materials of this system, but we kind of still need a charger. And so that's the concept here, to take a holistic picture of parts to see what's connected to what. It's not just about individual parts and their failure. Also important to note, it's very uninteresting when simple parts that are easy to replace fail. Even if they're highly predictable, that's kind of under control. The part that you want to figure out is not, how do I get more skin markers and measuring tape? What you want is to figure out what electronic subcomponent is going to become an issue at year 3 or when a certain thing happens. And so we'll go into a bit more detail about that. And so diving further into this example use case, this medical device has authentication and encryption. It communicates over Bluetooth through a computer or a phone to a server where the data is aggregated. So again, system view, there's computers now involved. It's connected to the internet. And so complicated. Taking a more generic view of how does this R&M data look, different R&M teams call their data store different stuff. So on the right, you see there's ERP systems, quality management systems, document management systems. Sometimes they'll call the thing that's doing the recordings a historian. Then you have like sometimes on-device monitoring, like health and usage monitoring system. These are the systems that are aggregating the data that you want to use to make your predictions about what we think is going to go wrong. Now, these systems have associated with them part numbers. Like you saw, there's like assemblies and sub-assemblies. And what we tend to see in the aerospace and defense context is these things called NIN codes or NSN. And those refer to the interchangeable parts. They're like a type of part, a spec for a part, not a particular implementation. We've got some other things that generate data. For example, built-in self-test. You turn on your car, it goes like, am I okay to drive? Things like that. And then failure codes. In your car, or aircraft, or medical device, as we'll see, you have these diagnostic trouble codes. And so lots of sources of data that we can think about when we do our predictions. So it's just good to see kind of what's the data terminology. And we're going to go a bit deeper on terminology. It's not going to take too long. So The area of failure is very well documented, and so I'm not going to dig into it too deeply, but it's important to know that there's more than one thing that can go wrong. And so you're going to need a different model for each type of failure. You don't want to have a model that says, am I going to have a bad day? Because maybe that model will just make predictions about easy to predict things. And it will ignore very narrow things. So we have to be aware that like there are different faults that lead to different failures. And when we say like, for example, I know that lots of tires are failing, you want to know the difference between like flat tires from running over spikes and tires that run out of tread and pop. Those are not the same failure. They don't have the same root causes. They don't have the same mitigations. And so we don't want to bundle too much together into one group of failures, because we'll get a not very meaningful model. It's going to be very generic if it's trying to predict too many unrelated things. And so what we're going to talk about today is more the stuff on the left, which is deep learning, machine learning models. The thing in the center here is kind of a weird hybrid. So survival analysis is quite pervasive in R&M teams, but we'll talk about it because it's quite pervasive in R&M teams, and sometimes it is the right solution. So we'll look at, based on how much data you have, what's the right fit solution for what you need. It is, though, important to express that this tends to be time series data, and time series data, like stock market data, is kind of horrible in that you're not making a simple prediction. You're making like a complicated prediction based on like how long ago did things happen. It's time series data is fancy and complicated, and so it's important to point out R&M data happens over time, not just at an instant in time. And you want to provide analytics. You don't just want to have a box that does its own thing. Humans have to maintain these systems, and so there is analytics dashboards, and you have to think about the human component, the human interaction. Survival analysis is a little interesting because you train on all the data. Whereas in machine learning, you do test train splits, and we'll go into that a bit deeper. But what you want to see here is that maintainers write notes, and so there's natural language processing. You also want to know, just is something weird happening? So that's outlier models. Classification is like, tell me what's going on. Is it A or B or C? And regression would be things like residual useful life. How much time do I have left on this part? What's your prediction of how much time is left? Or it could be, what's the probability of failure? Instantaneous failure, like the hazard function. And so these type of models is what we're really talking about in this presentation. So a few more quick terms. I'm not going to go too deeply into it. Sometimes this data is not fully known, so it could be left or right censored. We also have this concept of a hazard function that most of you will know, which is looking at the instantaneous, like now what's my risk of failure, that will follow a curve that early on things tend to be very risky because maybe the part was installed wrong and so high risk of things failing, or because of the wear out pattern, when they get really old, there's a high risk of failure. And in the middle, during the service life, you would expect the risk is less because the part's installed and running, and so that's like a general expectation. It's just good to express the type of models we're talking about come in two flavors. There's univariate models where you look at a variable, like how long has the part been in service, and you make a prediction about what's the probability of failure. That would be a univariate model. A multivariate model is where you look at different factors to make a similar prediction, like how much time is left on this part, or on this assembly, or on this system. And so we should also keep in mind that our prediction is a statistical prediction, not an actual guarantee. So the part may be fine, or it may fail when we didn't expect it to. And you want to have a quantification of what is that. But our prediction and our actual are never going to be exactly the same. The real world is random. And so things happen. Lots and lots of things as we go into this predicting failures world can go wrong. And I wanted to point out just 4 things that can go terribly wrong. One of them is the proportional hazards assumption, which says different parts will have, different of the same part will have kind of the same failure curve, let's say that bathtub curve. That may not be true. So if you have a fender that goes on the front and the back of your vehicle, they will not have the same risk of getting smashed up. And so even though they may be the same part number, they're not the same risk. They don't actually function the same. And so that's okay. You may just need to add a variable that says like, where is this part installed in order to make a prediction about like, when is it going to wear out? You also have this problem of a third variable problem where you see lots of good correlations, make a model that in theory works, but at deployment you go like, oh, this doesn't work because some third external thing was causing both my signal and my failure. So the example here is, germs cause bad smells and disease. If you use bad smell as a predictor of disease, you're not actually doing a causal model, you're doing a incorrect causation. And so that's always a risk. So you have to think about like, does my model make sense? Another one is learning from unusual history. You may think like, okay, so we're doing machine learning. Let's just like take all the data and just train on all the data. But sometimes you need to censor the data for weird stuff. In the defense context, you may have a history of a part, a widget, that you have the history of it getting blown up. You also have the history of it sitting in a warehouse and the history of it during training when they just like beat the crap out of it to test it out. You want to maybe have a variable for that or delete the unusual, there was an Iraq war that's not happening that same way again. Don't model stuff based on that situation, or maybe only model stuff on that situation. But we have to be aware that like our data has some specialness to it. And another very common problem is just not enough data. So sometimes you'll run into a situation where there's simply, when you do a join across a few different fields that you want to use in your predictor, less data than you expected. And that's a thing. And that may force you to use a simpler model because you have less data. Another problem is that sometimes stuff is not in the computer. It's on a spreadsheet or in a piece of paper. And so this is a real picture of the Neuraleve warehousing. Not everything is in the computer. Sometimes you got to do digitization. Another problem that we see is statistics. If we want to say like, what's the mean lifetime of a part? This is a famous example where the mean and standard deviation, both in the X and Y axes, is held constant to 2 decimal places, and even the correlation factor isn't moving. What they're doing is making teeny tiny adjustments to show whatever pattern, but keeping those things constant. This is a famous paper from 2017 showing that like you should probably look at your data. You don't just want to like rely on statistics alone because they don't tend to actually tell you what's going on. And so the opposite is also true. Correlation is very tricky, especially in the time domain. And so what I like to do is show people this picture and say like, what kind of stuff do you see? And so if you give this to a machine learning model, it's going to say, I see the blue is going down and the red is kind of constant. All the numbers on this slide are random. It's all made up. This is just random numbers. And so when you have a pie chart with big numbers like this, like big amount of samples, you start to see like, oh, it's random. But with 3 numbers, you're kind of led to believe like, oh, blue is common. But no, it's just you didn't sample enough. And so statistics actually are important. So at the same time as I'm saying statistics are a pack of lies, you also very heavily rely on statistics to do everything. So there is this like real uncomfortable relationship with statistics in the R&M field. Unfortunately, the null hypothesis here is also very strong. And so in order to say that our model is smarter than our datasheet, we got to prove it. And so we have to put on our science hat and go like, this is not a straightforward, I will implement machine learning and it will do better. We have to prove it to ourselves with data. And so what we're going to do is fly through some examples of data and some advice on data. And so particularly, we're talking about maintenance logs from maintainers that tends to contain a bunch of text. You've got the failure history over time of, there's a lot of different parts. They each have their own failure history. You've got parts orders, so going into the purchasing system and saying like, what did I buy and when did I buy it? And also sensor data. And as we'll see, these systems tend to aggregate lots of sensor data. In general, you want to have 300 plus samples of the thing that you want to make the prediction about. It's not an actual like provable number. It's our gut feeling of like what's a good amount of evidence to have to make a model about a particular failure mode, so that we avoid that problem of undersampling and not being sure. And it tends to be that you're not just looking for any failure; you're looking for like particular failures that are bothering the team, and that's the model that you want to build because it's something you know about that's either causing expense or risk or something. It's not random. It's not like let's look at every failure mode at everything. Um, and sometimes you have the best data for the thing you care the least about. But what are you gonna do? Okay, so when we go into a client, we're asking them these standard questions. These questions are called the 5 Vs. They're looking at how much data do you have? What's the nature of that data? What's the variety? And then how fast does it come through the system? Because that's going to have implications. So like milliseconds, seconds, years, hours. You also want to know, is this like simulation data failures? Is it lab testing? Is it actual recordings from historical data? How true is the data? And a good example of that in the R&M world is mentioned up here. Are the failure logs recordings of when the part was serviced and replaced or when it failed in the field? Those two dates could be really far apart. And so that goes to the veracity of the data, where you think that you're recording failure data, but you're actually recording maintenance data that could be N days separated from failures. And that's when you want to start to figure out, so what was that gap like? What's it usually like? What was it like in that office versus this other office? And then finally, is this the right data set? So some data sets you have, but they're not helping you solve your problem. And so this is the kind of thing that we go in and dig for. And having the answers to these questions helps to decide what should the project look like, as we'll see. You also want to look at external data sets. So what was the humidity in that place on that day, which you can connect to the data that you have. So let's say you don't have a humidity sensor, but you have a temperature and humidity and whatever data set just from public domain. You can join that in to help tell you more about what was going on during that time leading up to that time of this failure. So external data sets can be cool. What I decided to do here is looking at this medical device we talked about. We're going to go through 10 different data aspects. We could have gone through more, but I wanted to go through a pretty comprehensive list of the kind of things you see in this sort of reliability and maintenance project. And you'll see why, and then we'll go into the building models based on this data. But we start from the data. And so this is a example of how the data is stored. It's stored in a SQL database, and this is the query that returns these tables here that I stuck into Excel. What you see in this table devices failed is that over the years, going 2013 on the right down to 2014, 2016, over time, different standards for the serial numbers were followed. During the kind of approval phase, there was type a random number, like 123, 123. Then it got a little bit more professional as things start to, roll out. There's actual like serial numbers. But you see here a switch from these RMF, which is the manufacturer, to just M1000, which is the model number of the thing. It is extremely common when looking at device failure records that you have data cleanup to do. And so I guess the bottom line is don't expect clean data when you go digging for failure data from the maintainers. That's just it's not a realistic expectation. These things tend to go back years. And the person who was doing it before is probably not the person who's doing it now. And so let's now look at the next data set, which is sensors. These systems tend to have sensors that record stuff. In this particular case, this medical device is a brain stimulator, and so it records. This is data from a month ago. Zapping a real brain. And you can see it's a very sensitive reading of the output current and voltage. So this is a current stimulation device. So the current ramps up and is constant, then goes down, and the voltage goes up a little and drops over time to account for the impedance of the patient. And so this data gets recorded in a database. And we can use that to think about, well, this is what the device did, and then the device failed. What's the relationship between these two things? And so on an aircraft, you got a million sensors. This is like usable information. Then you got work instructions. They tend to be super detailed, and you can turn those words in documents like work instructions, and specifically the notes on the standard operating procedures into usable fields. So here's an example of a library that we wrote called Lazy Text Predict that calls some other libraries to figure out what model should I use for converting text into features. And so, excuse me, here we're looking at another data factor that's pretty common, called an anomaly report. And so the maintainer says like, hey, this thing went wrong. These two examples that I put here on the slides are a smashed screen and a bad firmware update. And so you can see that multiple devices are affected, and you've got some text-based notes here. And so you can use NLP to create features that you can use in your predictor. You may use something like count vectorizer to make features just using individual words, or you may decide to use transformers, like a much fancier and bigger model to understand the context of those words. But the point is that you have this text data that people are forced every time they do some maintenance to write stuff down. You can use that to like make predictions about future failures, about reliability. And so this is usable data. I wanted to go through some actual real examples of like what fails. Like we're talking about predicting stuff. What are we predicting? So here's an example of the little latch that holds the battery in. You can see it on the right-hand side. On the left-hand side, the spring broke. Another example, we saw early there about the mating cycles, like how many plug-in, plug-outs can you do? That's an example of a part that can, you jam in the plug too many times and you break it. On the right here, we see an example of an electrical failure, where the device has a nice little segregated failed sticker. So this is what we're talking about, like actual failures. The actual failures are a subset of a huge amount of potential real failures. These devices tend to be super well studied, so whether it's a vehicle or aircraft or a medical device, there are ISO standards that force you to think about every single possible failure mode, and I just wanted to show you that like there are many. And so it's only really a subset that the maintainers are fighting with every day that they're worried about could be a big problem. It's not actually the full list. The full list, a lot of these things never happen. They're like super theoretical, have to make up every possible failure mode that could ever possibly happen. But the maintainers and the operators are really interested in some specific subset, and that's where the energy gets spent. You also have physical location stuff. There's documentation on everything. In these like ISO controlled environments, you get to choose how much data you want to use because there's always more data. Like there's just so much documentation. And so there is a point where you go like, do I stop collecting more types of data and just focus on this initial subset that I have to make a model that's better than my spreadsheet? And then from there, I could add these features next. And so in the scoping, you want to have like kind of reasonable phased out stuff. But there could be things like the humidity at these different shelf levels could be different, and that could be affecting the reliability of this part based on like how high up in the shelving was it stored. So yeah, there's like no limit to how complicated you can decide the problem is. You also have the inventory data that tells you like how much stuff do I have. So if you have many, many, many of a part, it might be easier to just replace that part preventively on a regular basis. If it's cheap and you have a lot of them, why not? If it's a washer, go for it and maybe get a better washer, right? But it's critical subcomponents that you have to like desolder, resolder, redo testing that you kind of don't want to do that. And it tends to break down into these parts groups. So you see here there's class 1 medical device, class 2 medical device, and these are the assembly numbers, not the subassemblies. They have like a bajillion little subparts to them. Um, okay, so we're at data set 8 out of 10. Lots of different kinds of data, as you can see. This is a access log. And so sometimes you notice that why are parts breaking? Well, Jimmy kind of sucks at his job. And every time Jimmy logs in to use the device, he breaks it. Stuff like that. So you want to be able to find sources of problems that are like, oh, the driver of this thing, man, he really jams on the gas. It may not be a normal wear out pattern. It may be people. So that's something to consider. You have these access logs. Another thing to consider is you have many different kinds of audit logs, event logs, that you can go through and say, at this timestamp, this thing happened. At that timestamp, that thing happened. And you're over this time series going to start to put together a story. So here's one event log, and here's another event log. This event log has this little data column that's pretty interesting. What does this mean? Well, most of these systems have what's called diagnostic trouble codes. So they'll have a high-level message, something like connection quality, battery, but then they have these codes that go into a huge table. For example, in an engine, they'll have a million little engine codes. And so in this device, you have that as well. The standards kind of make these diagnostic trouble codes happen. That's kind of how it works. And so you expect to see diagnostic trouble codes, and sometimes they'll relate to your actual problem. And so in this case, these like codes here have another lookup table that tells you that ID was that code. And then you can do a relationship, as we'll see in a moment, between codes and then failures. So now that we've looked at 10 different data sets associated with a highly regulated device, let's see, like, how do we use it? I mean, great data, but that is the first part of the project. Now that you've got your data picture, you go like, all right, what can I do? So depends how much data. If you have tons of data, you can do a time series analysis. And that's one thing that we'll look at. If you have kind of less data, you could say, am I in a weird situation? And if you have just a little bit of data, you can do a standard survival analysis type model. Now, if you have a ton of data, you could do all three. But obviously, the fancy big data approach is going to get you the coolest results because you can have the most variables. And so let's kind of explain a little bit what is this magic supervised learning model stuff. So you have some observations from your data set of historical failures and data, sensor data, usage, whatever stuff you pick. And so your Y is your stuff that you observed in terms of failure. Your X is your stuff that you observed in terms of features of the part. And this is going to be specific to some failure mode because you want the model to be somewhat specific, not just like in general, are things going to go bad? And so to get a little bit more specific, you have to kind of engineer Y. So let's say Y is like days to failure. You have to take the data set for it failed on this day, and then for each observation of like day 1, day 2, day 3, do the calculation to get your correct Y. So there's a little bit of monkeying with the data, but it's not too hard. And then you get some kind of causal model that will try and make causal relationships between observations in the field and predictions in the field so that you can say like, oh, I'm out here and my red blinky light says, fix me. I'm not broken yet, but please come fix me. And it's better to have that, drive into the shop and fix that wiggly part than, well, I can't drive, I'm stuck. Similarly, in this medical device context, you don't want to like zap people's brains with a broken device. That would be bad. So again, going to the unsupervised models, they're a little weird because what you're doing is you're saying x equals f of x. It takes a second to get used to, but what you're saying is make me a model that can reproduce my data from my data so that I know when I'm in like a normal situation, when the distribution of my current data I'm observing is like expected, and when it's not expected, I don't know what's wrong. I know something's weird. And so I should probably have a blinky light for that goes, maybe take me into the shop. I don't know what's wrong, but like this is odd. Like an odd configuration of the data that we know about what's going on in the system right now. And that can provide value to the R&M team because it may mitigate failures in the field of even things we didn't think of. Just knowing something's weird could be very helpful. What's kind of cool also is you can use this for other stuff. Like you could use these features in a predictor, in a supervised predictor. Okay, so you do want to have some quantification so that you can say what good means. You don't want to just say good. You want to go like, here's what I did before the change, here was its performance, here's what happened after the change, and here's the performance. And there's two sets of metrics. One is these machine learning type metrics that tell you how did I do on my machine learning model. And then you have kind of business outcomes, like uptime. In my experience, the maintainers care a lot about the machine learning outcomes, but in the real world, nobody cares because when you leave science land and you go into engineering land, they really want to know the R&M metrics, not the machine learning metrics. The machine learning model is not learning in the field. It's done. Now it's like getting used. So you have classification metrics for example, fail yes or no in the next 24 hours, let's say. That would be a categorical binary variable that you're predicting. You also have regression variables like residual useful life. How many days do I have left on this thing? And so that can be measured with mean squared error. There's these different standard metrics. I'm not going to go too far down the road in a 1 hour talk. But the idea is you want to make decisions that are data driven and quantified, not it feels better, but you need numbers. Also, to get budget, you have to, say that you're going to measure before and after. And so time series is kind of the fanciest approach. And so when you're looking at these different failure modes, you go, okay, I have an expensive, risky, either or both failure mode. Let's see if we can figure out how to predict that thing in advance to mitigate that happening in the field. And so you want to know what's the prior, what's happening leading up to the failure mode. Unfortunately, there are situations where you have a correlation, like, hey, I see this trouble code when this failure happens, but it turns out it's maybe like a opposite relationship, like when the motor breaks, then it sets a trouble code, and you're like, great, but like it doesn't help me. Like I need to know stuff before the failure, not after. And so we want to know leading up to the failure what happens. And can I detect that stuff before it happens? So I put together here a little super crappy handwritten example of like, what does that look like? And we're going to go into it a little bit deeper. So this is the fancy stuff. And we can ask these narrow questions, like I have a particular thing, model it for me, or we can just dredge the ocean and go like, for feature and features, for failure mode and failure modes, try a whole bunch of stuff and tell me what you can predict. Those are both valid approaches to this. But it's good to know that these exist. One is like, let me just go broad and figure stuff out. And the other is, listen, dude, I have this one problem. Can you do this or not? And so this little graph here, what we're showing is at the 0 on the horizontal axis, that's when the failure happens. And in the vertical is a count of, in my whole data set, lining up all the failures 2 times 0, what happened just before that? And so I'm doing a count of, let's say, a group of diagnostic trouble codes. It might not just be one, it might be like 5 or 6 that I think are relevant to my problem. And if I see some kind of relationship like, ooh, bad things are being indicated before the part fails, that's pretty cool. That tells me that like, hey, maybe there's something here. Now, like I said earlier, you don't just want to print out the correlation to say like, is this slope going up? You also want to look at it with your eyes for the reason that we just talked about before. So you make a scatter plot kind of like this, and you look at the correlation factor, which is just a Pearson number. And together that tells you what's the story here? Is there value here? Do we proceed to maybe try and make a model? And so we've got this feature selection problem where we've got to figure out what things are reasonable to go into my model. And also critically, how long back should I look? Maybe it's like a week, a month, a day, a year. I don't know. And so like it requires some thinking about because we're dealing with time series data. It requires literally some experimentation to figure out like what's the most predictive time window to think about, and also what's reasonable. It could be deployments are a certain length, and you don't want to predict from before, or you want to have a clip at like the last maintenance event to say like, just trust me, the guys got it working at the last maintenance. Don't look back before that at anything that happened before the last maintenance. Um, and so, in general, the way that these model building exercises work, you have some tensor. It's like an array of samples by time series by features. It's kind of like this cube of numbers. And you have your outcomes, like failure events. So it could be days to failure, like we talked about. So you take this X and Y, and you can split it into it's like a deck of cards. You shuffle and split and shuffle and split. And that's called cross validation. And what you do is on your training data, you fit a model, and you then check on your testing data, how did I do? You tend to have actually like 3 sets. You have like test, train, validate, but this is the idea. The idea is you want to have some data that you didn't train on and see like, can I predict from that data? Now, you tend to split in 2 different ways. You want to split, let's say it's aircraft. You want to split by tail number to make sure that you're not like cheating by learning about that plane with some of the other data in the training data set. So that's one way of splitting it. You also want to split by time so that you don't like know everything about a certain year, because in your training data set, you have a whole bunch of other tail numbers from that year. And so you want to do both to make sure that like you're not cheating in the time side or in the I know that vehicle side. And so that gives you that like double split approach, gives you more confidence in what you're seeing, the generality of what you're seeing. And so just to go back to the basics, you want to make sure that on this X test that wasn't used for training, that you can make predictions that are real, that are useful, better than our spreadsheet. There we go. Okay, so we're going to look at 2 different approaches here to a multivariate model, like we just talked about. One approach is using big numbers. So I have tons and tons of data. I'm going to make my X be samples by 30 days by 3 numbers that I want to measure. So that's 90 numbers for each prediction that I want to make goes into my model. It's a lot of numbers. So you've got 90 of this, sorry, you got 30 of this X1, 30 of this X2, and 30 of this X3 that goes into making one prediction of how many days do I have left on my part, or for a particular failure mode. And so let's say this feature is the diagnostic trouble codes over the past 30 days. And each spot is like on that day, how many were there. Then you have how many sessions were delivered that day, and then how many sessions were delivered by staff with less than 1 year of experience on that day. And so if you can imagine, there's this, 90 numbers that you're using to make a prediction. So consider that this is what I would call like the big data approach. There's another way to do this. We can actually do the same kind of thing, but with 3 numbers, where we kind of engineer the solution by hand, and we go, okay, I'm going to make one number that represents the count in the last 5 days of those same trouble codes. Then I'm going to make another number that's like the number of sessions in the last 30 days clipped by the last calibration date of the unit. Like we talked about this clipping thing, you don't want to necessarily go back before you fixed everything up, because the data before that's probably wrong. And then you go like, how many sessions by unexperienced, less experienced staff happen in the last 30 work days. So like these are features that are highly engineered, and you've got a model that only relies on 3 numbers to make its predictions. What we like about that is that it's a pretty straightforward model. Now, this model that has 90 numbers at the input may be very sensitive to small changes because there's so many inputs. Whereas this model only has 3 numbers going into it, and so it's a lot less sensitive to little changes. And we want to have a stable model. And so neither of these approaches is wrong, but this approach takes way more effort because you have to do more thinking and feature engineering and trying things. I'm skipping over a lot of detail about things like normalization and scalars because they're kind of in machine learning land, but I want to give the basic idea. The basic idea is you have this data on maintenance, and you want to make models about that maintenance data. So with outlier detection, like we talked about earlier, you can try and figure out, am I in a weird situation? This could be used, am I in a weird situation, to predict if a failure mode is going to happen. And it may be that it holds hints of if a failure mode's going to happen. And so it's not a one size fits all tool. Now, what's kind of cool about this is that you can do a lot with outlier detection. You can say, how weird is the situation? You can do some simulation stuff. So I left a link here to some of our like related work in this area, but it's a pretty deep topic, this outlier stuff. Okay, so let's talk about survival analysis for a second. This is the much more common R&M technology approach, but sometimes this is your best option because either not enough data or because you want to compare approaches and just say, how well does this approach do compared to the other approaches? And so you tend to have a situation like this where you've got some categorical variable, like deployed in the field in storage unit, right? These like red and blue will be different conditions. And you've got some survival probability over time based on those different conditions. And this will give you a bit of a data sheet to think about what's the probability of failure, and you've got some confidence intervals. And of course, the further along in time you go, the less confidence you tend to have about your predictions. Predicting something a year from now is kind of hard, but maybe a minute from now may not be that hard. And so there's some nice libraries for all this stuff. You can ask questions in terms of survival about different levels. So it could be a part, it could be assembly, it could be like a whole bill of materials. And so this is a legitimate tool that can be useful in these R&M projects. Okay, so these models have certain assumptions. They tend to be reasonable assumptions, but it's important to realize that we're making them. So some of these models will assume, for example, that you have accumulated damage over time. Things never get better, they just get worse and worse until the part wears out. Think of like a tire. The tread never like grows back. It just gets worse and worse until it's gone. Not all parts work like that, especially if you're maintaining them over time. And so important to think about the assumptions that underlie, like the proportional hazards assumption, that underlie these models, because if the proportional hazards assumption is not true, these models, especially these univariate models, will be wrong. And so, yeah, there's like thinking involved. It's not just like, okay, take this library, use it. And if you do go to this library and read the documentation, you'll see that they have these big red warning signs of like, don't misuse me, please. I could be wrong. So important to think about that. Wow, this graphic did not work out. Okay, so I wanted to also include some demand forecasting explanation. This tends to be like step 2. When you've got your failure data, you can take your historical data and maybe even your external data that you're joining it with and use machine learning to predict what should my stock levels be. You want to make that prediction because the R&M team is not just responsible for nerding out about like when are things going to fail. They're also responsible for figuring out inventory levels. Like how much stuff should I buy? How much stuff should I hold in reserve? There's this hurry up and wait mentality where you want to be ready. And so you want to have some kind of a time series forecast that predicts in the future what will I need. Now, it turns out that's a fancy question. So I gave some links to some recent cool libraries, stuff that we've used, but I also wanted to just give a picture from like the example that they give on their website. Just to show you like what is this, okay? So if you have stock level that fluctuates based on demand, let's say you're at the base, you're just trying to save money, and then you're deployed and you're trying to like, have force readiness or whatever. And so there's different things happen at different times, and there tends to be these cycles involved over time. And so what these libraries are meant to do is to forecast what will you need, and then you can stock appropriately. So if you know my parts are going to fail at this rate, this is the stuff I'm going to be using my parts for because I'm going to be doing this stuff, then you can start to figure out like, all right, so I got to have in advance this many parts of that stuff over here in this location. And so that's the high level of what are these demand forecasting tools being used for. They're using the previous models that we talked about, specifically the failure models, to advise with some confidence intervals what should I have on hand? And then there's probably a safety factor that goes like plus 20%, whatever that number is. And so what we tend to see is that there's like a service level agreement between the maintainer and the operator, if they're not the same entity, that says like something about like you'll get paid this much if you have that much uptime, for example. And so that's why the person who's doing the maintenance wants to make sure they've got enough stuff, that they don't fall out of their SLA. There's no sense in being like way past your service level agreement, and you also don't want to be too close to the red line. So there's some, comfort factor. And so I wanted to make sure that we've got at least a few minutes for questions here. The big picture is these projects tend to be like multi-stage, starting with data, then solution architecture, and then testing out simple models, trying them out in production. There's like kind of a long loop of things that have to happen, but it kind of starts with what can we do better, right? And so that's what I wanted to leave you with is this idea that reliability can be done better than it was done in the past using these new techniques. And so with that, I think I'll open it up for some questions. Shan, if you want to pop open the questions thing. There we go, Ryan. Go for it. Request unmute. There we go. Thank you, everybody.
Thanks, Dan. So one of the first questions we have here is about offset obligations. So yes, we're very familiar with offset obligations. We do a lot of work with ITBs in Canada and as well as outside of Canada. So we are able to get a 5 times multiplier on consortium transactions. So we work closely with a number of different universities in order to put together those consortium transactions and meet those offset obligations. We can get an even higher multiplier with investment frameworks. So that's another option that's available as well. And in terms of the Canadian military, the AI is considered a key industrial capability, so we're able to get points on those types of engagements as well. So if there's any other questions, we'll go through them now.
Yeah, I see a question from Manny. Okay, so deploying models to production, things are changing. Used to be we would have to do like C++ hooks to do like embedded system stuff. We've actually done this with Docker now. So believe it or not, you can run a Docker container in an embedded system that's like mil-spec. It's pretty interesting. So yeah, things as far as like deployment to production, you tend to want to deploy these like systems connected to a little blinky light so that they can use the diagnostic trouble codes in real time. That's the ideal. If you're doing the normal R&M though, like just failure modeling of a part high level, then you can do that from the computer. You don't need to do that from the embedded system. But what's nice is these embedded systems are feeling less and less embedded. So yeah, it's a very interesting area. It's not static. It's actually changing over time, which is cool. Alex is asking, when we start from zero, do you have a good reference to know what we should log on vehicles, systems? Boy, that's a question. Okay, so my first piece of advice is log what's standard, because you may be able to use a third-party data set to get more data. If you're locked into your custom data set, you're responsible for getting all the data now and forever. But if you use standard protocols, you will very likely be able to either procure or just get for free more data than you can get on your own. So that's one place to start. And so as far as like data acquisition, you want to have a data warehouse. So if you're starting from scratch, think about data warehouse, specifically one that supports time series data, just to make your life a little easier. And a few other things about like what data you should collect. Of course, trouble codes are a good thing to be collecting, but they're unfortunately there's a long history of people throwing this data away. So like, you land the aircraft and it has like its whole history, not just of the flight data recorder stuff, but whatever else, low side data, whatever you can get your hands on. Storage is cheap. Just keep it, because you might find later that you're like, wow, this was actually super useful. It's hard to know what you're gonna want, and so yeah, getting at the data, if it can be low side, makes it easier. If not, then do the hard way. But yeah, when it comes to sensors and systems, what I've seen people do is sometimes they'll add a sensor because they realize there's a problem. For example, if something heats up and it doesn't have a temperature sensor on it, they stick a temperature sensor on it. And so like it's not just a question of what data do you want to record. Sometimes it's like, oh, design oversight fixed by rework instruction. And so it's not all about having the best AI model. Sometimes it's about using the data science to realize that you're doing something wrong and fixing it with a rework. If you think about it, that's like a very permanent solution to a predictable problem. If you can't do that, then yeah, you do the predictive from the sensors approach. But sometimes you find cool stuff. Like, what can I talk about here? Man, NDAs are crazy. Yeah, sometimes like you have a certain part installed in a certain spot that will just fail. And no way to do it other than predicting when you see trouble codes start to worry. Okay, so what platforms have you done predictive maintenance on? I'm able to tell you about this example. There's a bunch of stuff I can't tell you about. That was from Dharmesh Mani. Any thoughts or experience working with big IoT platforms like ThinkWorks, C3 Lot? I haven't worked with those two, but I have done. It's been a while, but I have worked on a large-scale solar project from the combiner boxes in the field, from multiple fields, aggregating data. Back in the days when Java was cool. And so, yeah, the kind of things that you see there is like you want a signal to go tell people to go cut the grass because the grass gets in front of the panels. And so you should be able to like preventively predict that the sunlight is going to be blocked by the grass. You don't have to wait and then go cut the grass. Very American problem. Since grass is not food, why are people growing it? But that's a conversation for another day. So yeah, big picture, we're able to work with these big data IoT systems. They're not that common. What we tend to see in these like R&M situations is that vehicle level is like very isolated and it's like n copies of system X. And then things get streamed into a historian, which is like the bigger data set that you do the analysis on. Sometimes they're literally carrying hard drives from like the system to the like data warehouse solution because everything's air gapped and there is no internet. Other questions?
Dan, these are the questions that we have in the Q&A panel till now.
Okay, great. So thank you everybody for coming to say hi. You've got the link to the slides here in my email. You can also reach Ryan at Lemay.ai. He knows all about the ITBs and all the fancy stuff. I'm the tech nerd, so I know about the AI stuff. But yeah, it's a really interesting time to be in a changing field. Machine learning is really shaking stuff up.
Great. Yeah. So thanks everyone for joining today. And what I'll do is I'll send out an email to everyone with a link to the presentation as well as the recording so that you can go through it again. And absolutely, if you have any other questions or you want to follow up, just feel free to reach out and we're happy to chat.
Thanks, everybody.